a lot more about the technical aspects, what are the assays, some of the bioinformatics tools we were developing. And we're a year on now, and as Oliver mentioned, a lot of partners are now using these tools to generate data. So we've got a lot more data now to talk about, and Oliver's team will be talking about some of that data from January and Mekong in the next session. And I thought I would tell you a little bit about some of the data produced by some of our other partners in the Asia Pacific, and particularly ones that I thought might be relevant for the GMS situation and that last mile to elimination. So I think everyone in the room is probably even more familiar than I am with the progress and the challenges towards malaria elimination in the region, and so I'll just go through these very quickly just to give that context. So aiming for malaria elimination by 2030 for all species, and we can see great progress here in this WHO map up until about 2020, and then of course we see this resurgence in cases. The other trend you can see in this WHO chart is if we look at the light turquoise bands, we can see over time those are decreasing in proportion. And we've heard a little bit about the talks from Laos and from Vietnam, that's of course because of reducing proportion of the malaria burden coming from falciparum, and actually I'm saying here mostly vivax, but I'm acutely aware that Vietnam also facing challenges with the malaria. But for the vivax case, we know that some of the challenge there is of course because of these dormant erythrozoites and that are particularly difficult to treat, and that make the species much more resilient to intervention. If we go back and we look at this resurgence in the last few years, and we take a closer look, we can see that a lot of those cases are coming from Myanmar, and that's of course very unfortunate for Myanmar with the political unrest and the contributions that's had to the resurgence and undoing the great gains that they've made. So unfortunate for Myanmar, of course, but also considerable burden as well and risks to the countries bordering Myanmar, including China, as Professor Dr. Kwan described, and is working on that area, and also for places like Thailand in particular. So there's cross-border transmission risk that's raised. We also know that Myanmar has a considerable burden of P.vivax, and that of course brings this potential of drug resistance. And in recent years, we haven't had a good idea of actually what the resistance situation in the region is. And we've also had today, Dr. Kao gave a few great examples of how in that last mile to elimination, outbreaks can become more predominant and bring those challenges as well and risk of resurgence. And then importation, I think Dr. Kwan actually gave us a nice overview of some of the challenges for Vietnam in terms of importation. Here, not talking specifically about cross-border, but those long-distance importations coming from outside of the GMS. And how critical it is to keep an eye on those in the last mile, and even in post-elimination settings. So in my talk today, I've got three components. The first is just to briefly remind you of the vivaxGEN assays, what type of information they create, so it gives you a flavor of what information you can derive, what actionable insights you can derive from that data. Then secondly, touching upon how we might use some of that information to guide optimal treatment, so diving into that huge challenge of the liver stage and relapse, but also touching upon new updates on blood stage resistance for vivax. And then we'll change gears a bit to looking at the more spatio-temporal utilities of these tools, so touching upon some of those challenges I've just mentioned around long-distance importation, cross-border spread, outbreak response, and last but certainly not least, can we use the genetic data to see how well we're tracking in effectively actually shrinking that malaria map? And throughout the talk, you'll see I've got these yellow areas where I've got questions. Because as I said in the beginning, the January Mekong community is an amazing forum to be able to get feedback. And so we really value your feedback to guide us to make sure we're actually generating useful tools. So onto the assays. As many of you will know, the vivaxGEN assays have 98 markers. 93 of those are microhaplotypes. we have one Plasmodium species confirmation marker, and we have 4 drug candidates. And those candidates are in these 2 genes, PBMDR1, that's been linked but not validated as a marker of chloroquine resistance. And we have a couple of markers in PBDHPS to inform on sulfadoxine resistance, and that one is indeed validated. We tried to add in the marker that's also validated for improvement resistance, PBDHFR, but it didn't fit in an original multiplex. But we're open to potentially bringing that back in if it's critical. The markers currently have a protocol with library preparation suited for Illumina, and we're also considering whether other platforms might be useful. But for the moment, we use Illumina. And the amount of DNA that we need is sort of 2 to 20 nanograms of DNA. And this has been shown through January NACOM to be suitable for dried blood spots, which is great. So I mentioned, as you'll have seen, most of the markers are these microhaplotypes. And I think I've shown this slide before, but just to briefly remind, microhaplotype is the little window of the genome where we have multiple SNPs. You can see here in these examples 3 SNPs. And when we look at them in combination, we can get a lot of information about genetic diversity. I've just shown 3 on the screen here, but we have 93 of these across the whole vivax genome. And in a nutshell, what that means is we have a great potential to distinguish one strain from another strain. So essentially fingerprint infections. But also really critically, we can look at how related infections are to one another. And so we can look at the connections between parasites, which is really important for spatial and temporal monitoring. And so because we can capture those 2 things really well, the fingerprinting and relatedness, the panel can inform on multiple molecular strains. Use cases, and you'll all be very familiar with this lovely figure generated by Oliver and others in January NACOM, really mapping out the genetic use cases. So as I say, vivaxGEN can address many of these, although you will note the tool symbol in the corner, and that's because some of these are still work in progress. But I think we're in a pretty good position even with what we have now. So let's have a look at the first area of optimizing treatment. How can we use this information to guide that area? So as we've already discussed a little this morning, when we think of vivax and treatment, of course we have to think about radical cure. That involves treatment to both the liver and blood stages. And we might argue that the liver stages is the particular headache for us in achieving vivax elimination. And we don't have effective molecular markers for any of the drugs, but perhaps that's not, for resistance, I should say, for any of the drugs, but perhaps that's not even the big concern when we think of primaquine into phenequine, where rather some of the bigger questions are around identifying treatment regimes that have good adherence and also good safety for patients who may have G6PD deficiency or heterozygous females. And so a lot of work's been done on the clinical front, clinical trials and cohorts. We may hear a little bit from Cindy and other experts on that front. And that's been really informative in guiding appropriate treatment regimes for different endemic settings, different scenarios. But there are some challenges in those trials. So when we do these trials, we're following the patient, of course, over a period of time, that might be say up to 6 months, to see who has recurrence. And we still have this challenge of distinguishing whether those recurrences are coming from failed blood stage treatment, recrudescence, deactivated liver stages, the relapse, or new infections. And we could try and simplify this challenge by saying, okay, relapse and recrudescence essentially are both treatment failures. And what we're really concerned about is separating those 2 from reinfection. There's some utility of genetics here to try and tease apart this picture, but it can still be a bit tricky. And that's because we know that with recrudescence infections often have the same strain as the day 0 case, and reinfections often would have a different strain in the day 0 case. But with reactivated liver stages, it's challenging because they may be the same or different to the day 0 case. And so this is where the ability of the microhaplotypes to capture relatedness really comes into play and is really helpful. So what we can do, and what we have been doing in several clinical trials of the primicline and tetranicline regime, is genotyping the pairs of de novo and recurrent infections to try and identify where they're close relatives. So things like, we refer to siblings, so like sisters or brothers. And this schematic here shows us that an example. We've got some siblings here. They have shared parents. So they're not different. So they are different to one another, but they are highly related. When we look more closely at their genomes, we can see that they must share parents. And that's important because if we get a mosquito bite from if this mosquito bites someone and it's got these siblings, one goes into the liver and forms a dormant epizooite, and the other goes into the blood. On day 0, we'll pick up the first one. At a later time point, if we have reactivation of the second one, we'll pick that up. And if we just took a close look, we'd say, well, these are different. So maybe it's a new infection, we're not really sure. But when we look more closely at their genomes and we see that they are related, we can see they come from the same family, and that tells us it's more likely one and not two inoculums. And so this is kind of a way for us to, I might use the word PCR correct for reinfection. It's not perfect, but it's certainly been helping us with our interpretation of some clinical trials and cohorts. But of course, today, we're talking about the Jen-Ray-Macon forum, and, the routine today. So you may be thinking, well, what's the relevance, especially if you're in the last mile to elimination, you may not be thinking of doing clinical trials. What's the relevance to the Jen-Ray-Macon forum? And that's actually a question I guess I have to you, is, do you see a utility of applying the same strategy for passively detected recurrences to classify whether they are relapses or reinfections? So, I guess the question is, could that be informative to give an idea of when you get recurrences, are most of them coming from relapses, questioning the treatment, or are a lot of them actually rather coming from reinfections? And if it does have utility, then I guess, the question that follows that is that we need pairs of de novo recurrent infections. We can't take a single time point to inform on this. So is that feasible within routine surveying? Maybe it is in that last mile to elimination because you don't have as many cases, and each case is really critical in that last mile. And perhaps in that time, it is feasible to look at things like hospital record numbers to try and connect pairs of infections. So food for thought there. Okay, blood stage resistance, as Oliver pointed out, this is a tricky one for vivax, with very few markers available and certainly validated very few. And so this is why our panel only has a couple of markers at the moment. There are some other candidates we could add in here. Pyramidine I mentioned, which is validated. PBCRTO, which is not validated, so questionable what we would do with that data. PBMRP1 I talked about last year, and again, it's unclear what its role might be and which drugs indeed might be implicated. So what I wanted to talk about today in a little bit more detail is PVMDR1 copy number and deletion and their potential role in methylquin. So the sort of first case, I might say, for the interest in PVMDR1 in GNS comes from a study we conducted with Professor Francois Nosten some years ago now. So this was conducted in Thailand, and we conducted whole genome sequencing and that other number of vivax isolates, and saw that a lot of them, 20% of them, had multiple copies of PVMDR1, which immediately raised some alarm bells, because PFMDR1 copy numbers associated with methylquin resistance, and methylquin was being used in the region at the time. And indeed then, when we looked at changes over time, we did see a drop in methylquin, in copy number after methylquin use was discontinued in the region. So that was quite compelling. You may be thinking, okay, but this is a pretty old study, 2016. And the reason why I raised this again is because there's actually a more recent study from Cambodia this time. This is still in preprint. This is a study by John Popovici's team from Institute Pasteur Cambodia and some of their collaborators in the US. They've looked at the genomes of some Cambodian isolates and seen that a large fraction of them have these deletions in the promoter region of MDR1. And interestingly, those deletions actually increase the expression of PBMDR1. So it's almost like a different mechanism of having more PBMDR1 protein. And importantly, they've shown that the parasites that have those deletions appear to have higher IC50 metastasis, indicating social methadone resistance or reduced infectability. And so that's quite compelling because we've got these two cases in the GMS region. So because of that, we've been looking into options for like how we might be able to type those variants. It's difficult to detect copy number variants in large deletions with Illumina, current platform, but we've been looking into long read sequencing assays as a potential option here. And yeah, well, again, we're interested to know how useful this might be and any other feedback. Okay, so let's change gears a bit and now look at the more spatial and temporal applications of surveillance. So we might start with the easy one, which is this long distance importation. So here we need genetic data or genetic markers to be able to separate parasites from long distances, and that's generally quite easy because parasites do tend to be more different the further apart they are. And so it's perhaps no surprise that the microhaplotypes do seem to do a good job at separating countries at these large regional levels and even at the national level in some but not all areas. In these areas where you have a lot of cross-border movement, like Cambodia-Vietnam border or the China-Myanmar border, that's still tricky. So we've been looking at this this use case in China. So this is where Professor Dr. Wang and Dr. Yao. And this is a very important use case for China, of course, because they've eliminated malaria. And so it's key that they can keep on track of importation and understanding where they're coming from. And we've genotyped over 1,200 cases from China, presenting in China, I should say. Those cases are those involve cases from the China-Myanmar border region and also some older ones from central China, and they're all given black dots in the spot. And then there are a number of suspected importations, which are all the different colored dots, the other colors of dots. And you can see generally there's pretty good separation actually here. Maybe in Myanmar it's a little bit harder. There's the dark blue spots that obviously can see my center, but there are a few dark blue spots that mix in China there. But for the other areas, actually seeing really good resolution. But I totally appreciate you may be looking at this figure and saying this is a really hard figure to interpret. And we think so too. And so we've actually been working on some classification-based tools, online tools. My colleague Anto actually presented some of these tools at last year's January Mekong meeting. So the way they work is that you upload your genetic information to an online web application, which then will run through an algorithm that will map against data from different countries and essentially say where your infection most likely came from and how confident it is of the prediction. We've got an example here of a Thai parasite, a Thai sample that actually looks like it came from Papua New Guinea, and the algorithm is very confident of that prediction. So we're updating these tools by increasing the reference sets and other optimizations. But one of the questions we have for the January Mekong Forum is, even this format may not be helpful, and so we'd love your feedback on that. We're also interested to know how quickly is the data needed. At the moment we're working with Illumina. How quickly do you need that feedback for your responses? And I guess the last point is not so much a question as a comment, just a note, as I mentioned earlier, that this approach may not work in all areas. It's certainly not good for mobile border areas. So that takes me to the cross-border utility. So for cross-border monitoring, as opposed to long distance, this is asking a lot more of our markers because we're now asking about, we're kind of zooming into the microepidemiology area. asking about movements of people really by land travel. So here it's good news that the microhaplotypes, even though we're asking more of them, do appear to have delivered, and we do see some evidence that they have good microepidemiological clustering. So for example, if we look at some data from these two sites in Vietnam, 300 kilometers apart, we can still see some pretty good clustering by site. If we zoom in a little bit more in Ethiopia, it's not as perfect, but you can still see pretty much site-specific clustering in these sites just 200 kilometers apart. And then here in Afghanistan, a couple of sites just 100 kilometers apart in this area, and again, pretty good separation by site. So we've taken these tools and we've been expanding our sort of reference map of genetic data so that we can understand more about importation but also cross-border transmission patterns. One area we've been working in is South Asia, this region shown on the map, and we've conducted genotyping in a number of the sites shown here. Here I wanted to particularly focus on Bhutan and what insights we've seen from cases we genotyped from Bhutan. This is Dr. Tokyo Gupta and others from the Vector-Borne Disease Control Program. So Bhutan, we know, has had this long history of cross-border transmission, cross-border movement even with India. And in a survey that we conducted some years ago, we were actually only able to enroll a number of patients who identified as Bhutanese nationals, about 60%, but also about 40% of cases who identified as Indian nationals. So when we genotype the cases from all of these different areas, we get this pattern here. It looks a little bit messy, but if you bear with me. So in the orange, we have cases from Bangladesh, and they're separating quite distinctly. And then at the bottom of the figure, we have this large map. And this reflects, I'm not sure if you can see my screen, but all of these high endemic sites in the western part of the map. So India, Afghanistan, Pakistan. And Bhutan is quite interesting because we can see, so they're in the red, and we can see the non-national cases, so those who identified as Indian nationals, mostly sitting with that large endemic cluster, while the Bhutanese nationals are actually separating out. And so that was really interesting that we could actually see maybe even a potential in some settings to separate national from non-national cases. But we know it's not always going to be like this. In fact, we almost get a teaser of what might be the more common situation in some areas with a lot of cross-border movement, with these two cases here that might reflect a kind of mixing between Indian and Bhutanese infections. And we know that could be, this pattern might be even greater in some border regions. And in those regions, we think it may be helpful to look at transmission chains to understand how infections have gone from one person to another, and whether we can map this across borders. And so we're working with Professor Dr. Wang's team to look at this more closely in that China-Myanmar border region. This is work with Dr. Shazia Rubal-Defensive. She's putting together a model framework where we can use genetics, but also combine that with epidemiological information, which is really key. And that might be features like, recent travel history, or contact with other people who've had malaria and other features. So it's still a work in progress, but I thought I would highlight it here because I guess one of the questions we have for the moment is whether this type of information might also be useful for the CNS region to understand the chain of transmission, potentially within or across borders. So outbreak response, for vivax is certainly a bit, in terms of what we can provide in the genetics front, what we can inform on is trickier than for falciparum, because we don't have, for example, effective drug resistance markers so that we can say this looks like it might be the key driver of the outbreak. But there are still some utilities of spatial tools here. And I won't go through this in too much detail because we had a lovely representation of the Mackay outbreak and the response of involved genetics in last year's January NACON meeting. But just to remind again of the potential of spatial applications to inform on outbreak response. So, as many of you will remember, Nakai district had pretty much no malaria since 2016, and then saw this outbreak of cases in 2023, all vivax cases. And Dr. Rita Rayburn and others from WHO, and also Dr. Keo and her team, elicited an outbreak response strategy, and that involved, of course, the serology, but also genetic investigation that our team at Menzies and January Mekong supported. And just to remind that the information we were able to obtain from this was, first of all, we could see that in blue here, that Nakai outbreak looked like it was driven by a single strain expanding very quickly. So that's something we can achieve from the genetics. And then when we had a closer look to see where it might have come from, having this broad data from January Mekong was really valuable to tell us that it looks like it's not a long distance importation, it really rather looks like a local one. That it looks like it's come from another endemic region of Laos, or potentially just across the border in Vietnam. And again here, we're keen to know if that type of information is useful for the local response activity, or are there other pieces of the puzzle that we can potentially add to support the control program and those responses. And I think that the situation with Nakai really highlights how useful it is to have a global or at least a regional map of genetic information. And so it's really good news that there are a number of partners who are now using the same microsatellite for microhaplotype markers. And so we're getting this growing map that we can use to strengthen our cross-border and even long-distance importation use cases. So last but not least, how can we use genetics potentially to tell us how we're doing, how well we're actually shrinking the map? And for this one, I wanted to share a little bit of data from a collaboration with partners in Cambodia, and the Institute has there. And so we know that Cambodia, of course, is aiming for malaria elimination imminently, and has had the challenges with vivax, and as a result, increasing the implementation of Primaquine to try and deal with these challenges. And it's, of course, really important to know how well we're doing. We can get information from case reports, but we don't always know what, at the bottom of the iceberg, are there sometimes asymptomatic or sub-patent cases. And so we did a pilot study with Professor Johan Popovici's team, including Ms. Rotain, where we looked at some cases from these two provinces, Rattanakouri and Mongolia, and we were looking at different time points, just for small numbers of cases to give us an idea of how well this might work. So they were genotyped at the microhaplotypes, and one of the first things we thought we would have a look at is how many different clones, or like how diverse is each infection, because we know this can give an idea of whether we have lots of superinfection in an area where there's a lot of malaria, people keep getting bitten, versus whether there's less malaria, so we have less multiple mosquito inoculations. And we can see here in the plot that indeed the numbers actually do roughly reflect the case reports. We see a bit of a peak here in 2019 that actually coincides with an earlier time point when there were challenges with village malaria workers being laid off and less activity on that front. That coincided with an increase in cases. But we see that this gets back on track by 2023, and we're seeing reduced polyclonality there. And also then if we look at the data in a different way and look at relatedness, the relatedness data also shows that if we look at the yellow dots in 2023, appreciate this is a little bit technical, but what we're seeing is we have a lot of connections in 2023 compared to, say, if we look at 2015, the blue dots, where almost no one's connected. And that's telling us that we're shrinking the malaria map, and so we're not having lots of these multiple infections that are then outcrossing. Rather, we're pretty much bottlenecking the population. So this is certainly interesting from our perspective as genetic epidemiologists, but we're crucially aware that we need to find a better way to translate this information so that endpoint users can find it more informative. And so that's certainly work that we need to do and work for us on our end, but we're also open to any suggestions from others. So to summarize, we see that the current assays can provide temporal and geospatial insight, but we need new assays for some of those drug candidates, like the MBL1 deletion copy number variants that I mentioned. But from January Mekong, it would be great to know, how useful is this actually in a pre-elimination setting, because drug resistance, low stage resistance might not be the number one priority. Second point, the current assays have this potential to prescribe to inform on relapse versus reinfection, but we need to have pairs of samples, and how feasible and how useful again is that in the last part of elimination. We've seen some major advances in monitoring of long distance importations and also starting to get a good handle on cross-border infection spread. But we'd love to know as well whether the type of information we're currently generating is actually going to be useful to inform local response activity. And I'm thinking maybe this third point might even be one we want to dive in after the January Mekong team actually have shown some of their exciting new insights on cross-border in the region. And then last, as I've shown with a few of the examples there, we can really strengthen what we can do about monitoring transmission, especially through cross-border challenges with coordinated partnerships in the region. So it's really great that we seem to have good coordination with many people using the same markers and sort of converging on